Hi guys, welcome back to Wong Chemistry channel. This video is the part 4 video of your 7.1. In the part 3, we discuss about strong acid and strong base. Therefore, in this part 4 video, we will discuss about weak acid and weak base. Alright? So here is a list of your weak acid and weak base that you can take it as a reference. This is roughly your weak acid and weak base that you might always come across. Okay? So what makes your weak acid and weak base different from your strong acid and strong base? The first difference, they are weak acid and weak base because they will only dissociate partially in aqueous solution. Means that if I have 100%, there will be only maybe 0.1% dissociated. Alright? But different from your strong acid and strong base. If you remember in your strong acid and strong base, your strong acid and strong base will be completely dissociated. Alright? Means if I have 100 acid, I will form 100 H+. But in a weak acid and weak base, I might have 100 acid, but I only have 1 H+ form. That is our dissociate partially. Only a small amount of acid that will break into H+. Only a small amount of your weak base that will form your OH-. Okay? That will then result to your degree of dissociation is less than 1. Okay? And your percentage of dissociation will also be less than 100% because they only dissociate partially. Okay? So we know that they won't finish. Not everybody will turn into product. Okay? That's why the degree of dissociation won't be 1 and it will definitely be less than 1. Okay? So an example of our weak acid, your HNO2. That is my weak acid. When it's a HNO2, it's a weak acid. But when it's a HNO3, that is my strong acid. Okay? So make sure you can differentiate that. So you have your weak acid HNO2 over here that will be partially dissociate to form your H+ and also your NO2-. So initially, I might have 100% of my weak acid having 0 of my product. As we all know, initially there is no product formed yet. But final, what happened in the final is your weak acid will only dissociate partially into the H+. That means I might only have 0.5% of H+ form. Okay? And your HNO2 will left with 99.5%. Can you see that? Alright? So that is what we mean by partially dissociated. Okay? Your weak acid, only a very small amount of your weak acid that will break into your H+ and your NO2-. Okay? That's why your reaction over here is a reversible reaction because your acid, your weak acid over here, will not change into product 100%. Okay? That's why it's a reversible reaction where your reactant, your weak acid, will not finish. Okay? Alright? Simple. Next, we have an example of your weak base over here. And the same thing you can see is still a reversible. A reversible means your initial will not finish. Let's say I start off with a 1 molar weak base. We know that the final, you will still have the final of maybe 0.95 molar. Can you see that? You will have your weak base remain at the end of your experiment. It won't be converted 100% to your OH-. So your OH- at the initial might be 0. At the end of the experiment, your OH- could be only form 0.05 molar. Okay? So the main difference between your weak acid, weak base and your strong acid, strong base is their dissociation. Your strong acid and strong base will be dissociate completely, while your weak acid and weak base, they will only dissociate partially. Okay? Partially means only a small amount of your weak acid and weak base will break into the H+ and the OH-. Therefore, you will have your weak acid and also your weak base left at the end of your experiment. They won't finish because they don't have the ability to completely dissociate. They only can dissociate partially. Okay? Next, let's look at the Ka and pKa value for your weak acid. Knowing that your weak acid is a reversible reaction, therefore you will have your equilibrium. Okay? Knowing that you have your equilibrium, that's why you have your equilibrium constant with the respect of acid. By using this example given, let's write the Ka for the weak acid. So Ka, the same as your Kc, Kp. Your Ka will be your product over here to the power of its coefficient over the reactant to the power of its coefficient if there is any. Okay? So Ka will always in the respect of concentration. So your product will be in the concentration of your H plus times the concentration of your NO2 minus divided by the concentration of HNO2. So why are we taking everyone? Because everyone is in aqueous. Since everything is in aqueous, therefore your Ka will take count of everything. Bear that in mind is the product versus the reactant. Okay? And how about pKa? pKa is as simple as equals to negative log Ka. It works exactly like your pH. If you have your pH is equals to negative log the concentration of the H. So pKa will then be the negative log of the Ka. Okay? Simple. Let's try another example over here. It's the same thing. I still have my weak acid. We are still going to write the Ka. So looking at the equation, that is my aqueous. I will take it. That is my liquid. So please ignore the liquid. It's an aqueous. We will take it. It's an aqueous. We will take it. Make sure the equation is balanced. Okay? Therefore, from this chemical equation of my weak acid, my Ka will equals to my product CH3COO minus times the concentration of H3O plus over the concentration of CH3COOH. That is the dissociation of my weak acid. And you can see that my weak acid dissociated means my weak acid will be forming my H3O plus. So it dissociated to form the H plus. Okay? And everything is to the power of 1 over here is not because it's fixed. It's only because in your balance equation, all the stoichiometry is 1. And as we say above, if that is my Ka, then my pKa will then equals to the negative log of your Ka value that you just calculated. Okay? And very quickly before we move on, if you look at it, your concentration of H plus is directly proportional with the Ka. Can you see that? The concentration of your H3O plus is directly proportional with your Ka. Agree? So in the other words, if the acid is a stronger acid means I will have more H plus. Agree? So when you have more H plus, what happened to the Ka value? The higher the H plus, the higher the Ka value. The same thing over here, the higher the H plus, the higher the Ka value. They are directly proportional. So the stronger the acid, the higher the H plus, the higher the Ka value. Okay? Simple. And the exact same thing will apply on your weak base. Let's write the Kb value for your weak base. Same thing, your Kb will be the product over here. Everything on the product to the power of their coefficient. Everything is in 1 at this moment. Over the reactant to the power of its coefficient. Slightly different right now is a Kb. Kb because it's a base. Kb because we are having OH minus. Okay? So Kb equals to the concentration of NH4 plus times the concentration of OH minus over the concentration of NH3. And you can see over here, we are ignoring the water because it's a liquid. Can you see that? Same thing to the pKb. Your pKb will be equals to the negative log of your Kb. Exactly the same as your Ka just now. Alright? And what will happen to the Kb value when it's a stronger base? When you are a stronger base. Stronger base means what? Stronger base means you will produce OH minus more. Okay? So when you have a higher OH minus, what happened to a Kb value? Directly proportional. The higher the OH minus, the higher the Kb. So stronger base means higher OH means higher Kb. Can you see that? Simple. So another weak base over here, but the concept is exactly the same. taking the product CH3NH3 positive to the power of 1 times OH minus to the power of 1 over with the CH3NH2 base, and that is my weak base, okay? And why we ignore the water? Because your water right now is a liquid, so we will ignore the water. Therefore, we will only take count of all the aqueous that you have in your chemical equation. And once again, it will be proven if your base is stronger, alright, if your weak base over here is a stronger weak base, then you will have your OH minus higher. When the OH minus higher, your Kb value will also be higher because they are directly proportional. The higher the Kb value, the stronger the base. Okay? So I hope you can see the difference. When do we use Kb? When do we use Ka just now? Kb because we have the presence of OH minus, as you can see. And we will be using Ka when we are talking about acid with the presence of H plus or H3O plus. Okay? Let's take a quick look between the relationship between your concentration of H plus, your pH value, your Ka value, and your pKa value. So what happened to all this value when the acid that you have right now is stronger? Stronger acid means you will have a lot of H plus or you will have a lot of H3O plus produced. In the other words, the concentration of your H plus or H3O plus will be high. Agree? Okay. If the concentration of H plus right now is so high, what will happen to the pH value? pH equals to negative log of the concentration of your H plus. So right now, the concentration of H plus increased. What do you think happened to the pH value? Guys, it's a negative log. Do you know what is negative log stand for? It will make your value inversely proportional. So the higher the H plus, the lower the pH value. Therefore, when the concentration of H plus increase, the pH value will decrease. Okay? But what happened to the Ka value? Ka value just now is directly proportional with the concentration of H plus, if you remember. Okay? So the higher the H plus, the higher the Ka value. So right now, Ka value increased. Alright? So when the concentration of H plus increase due to a stronger acid, the pH value will decrease, but the Ka value will increase. Then what happened to the pKa value? pKa value equals to negative log of Ka. Remember the negative log, guys? The negative log will cause an inversely proportional. So when the Ka value is so high, that means the pKa value will be extremely low. Okay? So right now, if your weak acid is slightly stronger than the others, that means your weak acid will have a higher H plus value with a lower pH value, with a higher Ka value, but a lower pKa value. Okay? So when the acid is strong, this is the relationship between the four numbers. Make sure you know this very well to prepare yourself for your objective question. How about for the base? So for the base, we will talk about the concentration of OH minus. We will talk about pH value. Your Kb value is a base, and also your pKb value over here. So how should all the value look like when the base that you have is slightly stronger than the others? Stronger base means more OH minus. Agree? And higher OH minus over here also represent a concentration of H plus decrease. It's a base, guys. It's a basic. So the things that you should have extra in your beaker will definitely be OH minus. Therefore, in a base, the H plus is very little. When the H plus is very little, bear that in mind, pH is equals to negative log concentration of H plus. So right now, the concentration H plus decrease because it's a base, right? So the concentration of H plus is very low. Therefore, pH will be very high. And that is the reason why your pH will be more than 7 when it's a base. Okay? How about pOH value? pOH value will be very low because the concentration of OH minus is extremely high. Can you see that? And if you remember when we write the formula of your Kb by using the chemical equation, your Kb is directly proportional with the OH minus. In the other words, when you have a higher OH minus due to a stronger base, then your Kb value will also be higher. Okay? But the pKb value, which is inversely proportional, will be lower. It will be inversely proportional because your pKb is equals to negative log of your Kb value. Okay? So this is the relationship between your OH minus, pH value, the Kb, and also the pKb value for your base. Okay? When the base is stronger, the OH minus that you produce is higher. Therefore, the pOH is lower. But the pH is higher. Okay? Because it's a base. And the Kb value will be higher. The higher the Kb value, the stronger the base. Vice versa, the pKb value will be lower. The lower the pKb value, the stronger the base. Okay? So make sure you remember the relationship between all this. Okay? And next, we can relate your Ka and your Kb. Very simple formula. Your Ka multiplied by your Kb will be equals to your Kw. Remember your Kw? Your water ionization. Okay? And if you remember, your water ionization is a constant. And this constant at 25 degrees Celsius, your Kw is 1 times 10 to the power of negative 14. So when do I use this formula? Why do I need to know this formula and when am I going to use it? Simple. If the question gives you about acid, alright? If the question started everything with acid and blah blah blah. But in the question gives you Kb value. So can you use the Kb value for the acid? No. You cannot use the Kb value because it's an acid. So by using the Kb value given, you need to change to Ka value by using this formula. Alright? By using this formula. Makes sense? So be very careful when the question talk about base. Make sure the one that we have is a Kb. If the question talk about acid, make sure the one that we have is a Ka. And if the question did not give you what you want, then you need to use this formula to change to Ka or Kb that you are looking for. Okay? Simple. And the last thing before we go into the calculation of the pH of your weak acid and weak base is your percentage of dissociation. Why do we need to calculate the percentage of dissociation in your weak acid and weak base but not the strong acid and strong base? Because your weak acid and weak base is only dissociate partially. When we say partially, the question will be asking how much has been dissociated. What do you mean by partially? 5%, 10%, 20%, all that is also partially. So knowing that your weak acid and weak base would only dissociate partially, therefore the question can ask you to look for the percentage of dissociation. How much has the weak acid changed into H plus, or how much the weak base has changed into OH minus. Okay? And bear that in mind when you're doing the calculation, the degree of dissociation must be less than 1 and the percentage of dissociation must be less than 100%. Okay? Simple. Last but not least, the formula of the percentage of dissociation over here is very similar as what we have used before. Dissociated also means by reacted or used. Therefore, the percentage of dissociated will be equals to the concentration of the dissociated or change divided by initial times 100%. And the percentage of dissociation over here is not necessary in concentration. Your percentage of dissociation also can be in the number of mole. Alright, you can use number of mole to calculate the percentage of dissociation. It doesn't really matter. Okay, just make sure all the unit is the same. And please bear that in mind, the percentage of dissociation is only for your weak acid and weak base because they will only dissociate partially. If it's a strong acid, strong base, no need to calculate. We know that the percentage of dissociation is 100% for the strong acid and the strong base. Okay? Simple. So next, how can I calculate the pH for my weak acid? Very simple. To calculate the pH of the weak acid, the first and foremost, you must be able to write the balanced chemical equation for your weak acid partially dissociated. You need to know that your weak acid will break into what product. Okay? And make sure you balance them. The second step, we will then need ice table. Alright, I'll show you the ice table. If you remember the concentration initial, your concentration change and also the concentration equilibrium. Of course, you can use in the term of number of mole, also acceptable, okay? And for the weak acid, we need to have the formula of your Ka by using the chemical equation that you write in your step 1. So by using that chemical equation, you are going to write your Ka value and substitute in the concentration at equilibrium. And then you are going to solve the mathematics to find the X value, okay? The unknown value that we are looking for in your ICE table. After you have identified the X value, then we can use it to determine the concentration of H+. And at the end of the day, when you have the concentration of H+, what do? Simply calculate the pH value by using the formula of pH equals to negative log concentration of H3O+. Same thing, okay? So let's try the first example over here. Calculate the pH and also the percentage of dissociation of 0.23 molar of your HNO2. So knowing that your HNO2 over here is a weak acid. How do I know it's a weak acid? First and foremost, because I remember. Second, because Ka is given. You need to know that for a strong acid, there is no Ka, right? So whenever Ka is given, straight away we know this guy is a weak acid. Okay? Simple. So the first step is to write your balance equation and dissociate your weak acid. You have your HNO2 aqueous. Make sure the arrow is a reversible arrow because it's a weak acid. Breaking into your H+ aqueous and also your NO2- aqueous. And this concentration of 0.3 molar is the concentration at initial of your HNO2. Therefore, substitute into the ICE table with the concentration initial, then your concentration change, and last but not least, the concentration at equilibrium. Okay? Knowing that your HNO2 started with 0.23 molar. Remember the initial is given there. So your product right now is 0. I don't have the product. Okay? So when you don't have the product, what happened to the changes? Next, what happened to the changes? Since your HNO2 is a reactant over here, and it will dissociate when the reaction started, therefore the change will be minus X. Minus represent it has been used or reacted. Over the product, you have your plus X and also plus X. Everything is in 1-to-1 ratio because your acid is in 1-to-1 ratio with the product. Okay? And that will give rise to your equilibrium 0.23 minus X. 0 plus X equals to X. 0 plus X equals to X. The next step is to write the formula of your Ka. By using the equation, your Ka will then equals to the concentration of H+ times the concentration of NO2 minus over the concentration of HNO2. Your Ka over here, 7.5 times 10 to the power of negative 6, concentration of H+, X, concentration of NO2 minus X as well. HNO2 over here will be 0.23 minus X. And since the Ka value given is very small, your Ka value right now is times 10 to the power of negative 6, which is very small. Bear that in mind, if your Ka is smaller than times 10 to the power of negative 4, we can assume the X is very small. So we will assume X is very small. Therefore, 0.23 minus X will then equals to 0.23 over here. See that? So, it will then make your mathematics much easier. You will have 7.5 times 10 to the power of negative 6 equals to X squared over 0.23 because we have solved it. Okay? And from that, you can calculate your X value. And the X over here calculated is 1.3134 times 10 to the power of negative 3. That is the X that we calculated. And the question asking for the pH value. So if the question asking for the pH value, we need the concentration of H+ at equilibrium. Okay? Therefore, concentration of H+ at equilibrium equals to X. X equals to 1.3134 times 10 to the power of negative 3. As a result, the pH value will then be negative log concentration of H+. Substitute in the H+ that you have calculated, 1.3134 times 10 to the power of negative 3. Therefore, the pH value calculated is 2.88 over here. Simple, easy. Next, the question asking for the percentage of dissociation. So, we know that the percentage of dissociation is definitely for your weak acid or weak base. Therefore, we will only focus on this initial and also these changes for the percentage of dissociation. So, change over initial times 100%. And the change over here is X. The initial over here is 0.23 times 100%. Knowing that the X right now is 1.3134 times 10 to the power of negative 3 over 0.23 times 100%. Therefore, the percentage of dissociation calculated is 0.57%. Okay? So that is the pH value calculated for this question and the percentage of dissociation calculated for this question. Okay? And please make sure you know how to do this ice table, and also make sure you understand why the ice table looks something like this. In the weak acid, we have the presence of ice table and also the initial change and equilibrium because they only partially dissociated. So when they are partially dissociated means you need to know what is left at the end of the dissociation. Okay? We need to know how much of the acid, of the weak acid, has dissociated into H+, and also how much have left. That is the reason why you use ice table. Okay? And before we move on, just a kind reminder, your Ka is very small. It means if your Ka over here is smaller than times 10 to the power of negative 4, means negative 5, negative 6, negative 7, and all, we will assume the X over here is very small. Therefore, when your initial minus the X, it will then back to the initial. Okay? So we can do this assumption, then you can avoid doing your quadratic. Okay? Simple. Another example over here is the question asks you to calculate the pH of a 2.5 molar of C6H5COOH given the Ka. Same thing over here, I have a weak acid. Alright? And this is the concentration initial. Question asking for the pH value. Knowing that it's a weak acid, so your pH calculated must be less than 7. Okay? And the Ka given is times 10 to the power of negative 4. Therefore, no assumption. We cannot do assumption. You need to do your quadratic. Okay? Starting off our solution with the chemical equation of the partially dissociation of your weak acid. So you have your C6H5COOH aqueous that were partially dissociated, that's why it's a reversible arrow, into your conjugate base. So you have your C6H5COO minus aqueous. And definitely the presence of your H plus proton that will show the acidity. Okay? And your ice table was starting off with your concentration initial, moving to the concentration change, moving to the concentration equilibrium. Alright? The initial starting off with a 2.5 molar of your weak acid, where your product will be 0 because none has been produced. The change will be a minus X in this case, plus X and also plus X. Okay? Your concentration equilibrium as simple as 2.5 minus X, 0 plus X, therefore you have your X and your X over here. Next step, we are going to write the formula of your Ka. Ka will be equals to the product over the reactant, so you have your product C6H5COO minus concentration times the concentration of your H plus over the concentration of your C6H5COOH. Alright, your benzoic acid over here. Substitute in the value of your Ka 4.3 times 10 to the power of negative 4 only equals to your X multiplied by your X over 2.5 minus X. So the problem arises is your 10 to the power of negative 4. When it's a 10 to the power of negative 4, we know that when your Ka right now is times 10 to the power of negative 4, that means we need to solve the X by using quadratic method. So the quadratic method is as simple as your 2.5 minus X, you are going to times with your 4.3 times 10 to the power of negative 4 equals to your x squared and solve the quadratic, you realize that the x calculated having two values. You will have your x1 and your x2. Your x1 calculated is 0.0326, while your x2 is a negative 0.0330. And the moment you have a negative value and a positive value, the negative value will straight away be ignored and we will take count of the positive value x. So this is my x, okay? Next thing, the question asking for a pH. So to find the pH, we need the concentration of H plus that form. So concentration of H plus at equilibrium over here is equals to x. Therefore, concentration of H plus will then equals to your 0.0326 molar. Okay? Because your concentration of H plus is equals to x, x is equals to 0.0326 molar. And when you have the concentration of your H plus already, we can easily calculate the pH value. pH will then equals to your negative log concentration of your H plus. And you substitute in the value of your negative log 0.0326 molar. Press your calculator and find the answer. The answer that you calculated should be roughly about 1.487. And that is the pH value of our weak acid over here. And as we promised, the pH must be less than 7 because it's a weak acid. And there you go. pH equals to 1.487. Okay? So that is how we calculate the pH value of your weak acid. Anyway, we are still using this formula to calculate the pH. Just we are finding the concentration of the H plus slightly different. Make sure after 2 examples, you already know how to use this ice table. This ice table is extremely similar to the one that you learned in your topic 6, alright, in your chemical equilibrium. Alright, simple. Next, how about the pH of your weak base? And looking at the word weak base, knowing that we're actually getting OH minus over here. OH minus, like we have learned previously, you can only calculate the pOH. So from the OH minus, you only can calculate the pOH. But now the question asking for pH. How can I calculate the pH value of a weak base? Let's look at the step. The step 1 is still definitely write the balanced chemical equation of your weak base partially dissociated. Knowing that your partially dissociate will be using your reversible arrow. Okay? Then we are going to again use your ice table. Put all the information that you have into the ice table that you are going to do later. And then we are going to write your Kb formula and substitute the concentration at equilibrium because Kb is already at equilibrium. Okay? Solve the equation to find the x, whether using quadratic or whether using assumption depends on the Kb value. If the Kb value is bigger or equals to times 10 to the power of negative 4, then we are going to do quadratic. Okay? If your Kb value is less or equals to times 10 to the power of negative 5, then we are going to assume. Okay? Simple. And from the x just now, you can find the OH minus concentration. And from the OH minus concentration, guys, the first thing that you can calculate is pOH. Then only you can calculate the pH value. See that? So whenever we are talking about base, make sure you are calculating the pOH first. Because in the base, we are having the OH minus rather than the H plus. Okay? And of course, the formula that we will use is your pH plus your pOH equals to 14. Simple. Right? Easy. So the calculation for the pH of your weak base is very similar as the one for your weak acid. Just one more extra step because you need to find the pOH first before the pH. Okay? Alright, let's take a look at this example. Calculate the pH and the percentage of dissociation. So we have 2 questions over here. One is the pH, one is the percentage of dissociation. Of 0.8 molar of ammonia. 0.8 molar of ammonia. Ammonia is a base, right? So if ammonia is a base, then you will have the OH minus. From the OH minus, you can calculate the pOH. Then only you can calculate the pH. Agree of the flow? Simple. And the question given to you is Ka. Can you see the trick over here? Knowing that this is a base, or in more detail, that is actually my weak base. So ammonia is a weak base, and then the question gives to you Ka. So what do we need to do is definitely to find the Kb equals to how much. Okay, it's a base. We definitely need to use the Kb. We cannot use the Ka. Alright? Therefore, the relationship between Ka and your Kb is your Ka times Kb equals to Kw. Alright? The Ka is given 5.6 times 10 to the power of negative 10 times the Kb that we are looking for. Kw is 1 times 10 to the power of negative 14 as a constant. From that, you will be able to calculate your Kb value. 1.7857 times 10 to the power of negative 5. Okay, simple. Since you have your Kb value found, then let's move on to the next step. The next step is definitely writing the equation of your weak base. So you have your ammonia over here in aqueous with the presence of water in liquid, partially dissociate to form your NH4 plus aqueous plus OH minus aqueous. Concentration initial, concentration change, and also concentration equilibrium. Starting off the concentration initial with 0.8 molar of your ammonia. Your water will be ignored because it's a liquid. NH4 plus aqueous as a product is 0. OH minus as a product is 0 in the initial. So the change over here will be minus X. Water once again ignore. Your NH4 plus will be plus X. Your OH minus will be plus X. Your equilibrium will then be easily 0.8 minus X. Your water once again ignore. Therefore, your NH4 plus is a X, your OH minus is a X. Alright, so next, what do? We are going to use the Kb value that we have calculated and find the X. So we need the formula of Kb. Kb will then equals to the product, your NH4 plus times with the OH minus over the reactant. And since water is a liquid, therefore we will ignore the presence of water and only take the ammonia. Okay, Kb value calculated 1.7857 times 10 to the power of negative 5. Concentration of NH4 plus OH minus and also your NH3 at equilibrium is as follows. So substitute into the equation. So the next question, are we doing assumption or are we doing quadratic? Times 10 to the power of negative 5, guys. Do we need to do quadratic? No, we can do assumption. Since Kb is very small, assume X is very small as well. Therefore, 0.8 minus X equals to 0.8. Simple. And when you have this thing down, then your mathematics will be much easier. It will then become 1.7857 times 10 to the power of negative 2 equals to X squared over 0.8. Okay? We make your mathematics much easier by doing this assumption. Solve the mathematics, then you will get your X over here. Your X calculated is 3.7796 times 10 to the power of negative 3. Okay? Simple. Easy. So knowing that your X is also the concentration of your OH minus at equilibrium. Okay? Therefore, we know that the concentration of OH minus also equals to 3.7796 times 10 to the power of 3. So the next question over here, can I calculate the pH value that requested by the question straight away? No, because you are having OH minus. So when you're holding OH minus, the only thing that you can calculate is your pOH equals to negative log concentration of your OH minus. See that? Simple. Substitute in the value, negative log, press your calculator correctly, 3.7796 times 10 to the power of negative 3. When you press your calculator correctly, the pOH value is 2.4226. Agree? Simple. And guys, that is only the pOH value. The question asking for pH. So what would be your pH value? The pH value over here will be 14 minus pOH. So you will have your 14 minus 2.4226 As a result, the pH value calculated is 11.5774. And that is the pH value calculated in this question requested by the question. Okay? Bear that in mind, your ammonia is a base, therefore the pH value must be more than 7. So your pH value is more than 7 right now. Simple. Okay? Next, the question asking for percentage of dissociation. So how do I find the percentage of dissociation? The change divided by the initial. And the change over here is equals to X. And we know that your X is equals to 3.7796 times 10 to the power of negative 3. Your initial given in the question 0.8 times 100%. Therefore, the percentage of dissociation calculated is 0.47%. That is how much your weak base dissociated in your aqueous. In the 100%, you only have 0.47% that will produce OH minus. And that is the reason why it become a weak base. Okay? Too little of OH minus has been produced. Okay? So the biggest trick of this question is the question giving you a weak base, but the question giving you a Ka value. So you need to be very careful. Knowing that it's a weak base, therefore you need to find the Kb value. So first and foremost, you need to change the Ka into the Kb value. Okay? That is the biggest trick. Alright? And that's it about this question. Simple. And let's try the last example for this video. Slightly different. The question is asking you to calculate the concentration of hydrazine solution. So we are actually looking for the concentration of hydrazine solution initial is how much? Because the question saying that the solution having a pH of 9.75. So the Kb value is given. Knowing that the N2H4 is a base, or in exact is a weak base. So if it's a weak base, the things that I need is a Kb. I have the Kb value given correctly. So good enough. But the question giving you pH. Knowing that it's a base, I have OH minus. Therefore, I need to find the pOH value rather than the pH. Therefore, the first step for this question is to find the pOH value. pOH equals to 14 minus pH. So your pOH is a 14 minus 9.75 given in the question. The pOH calculated is 4.25. That is our pOH for this weak base. So please make sure you know that this is a base. And in the base, I need a Kb and a pOH, not the pH. Okay? Next, we are going to do a ice table for your hydrazine solution because we are looking for the initial. So you have your N2H4 aqueous plus the presence of water liquid will dissociate partially into N2H5 positive aqueous plus your OH minus. You will need to release a OH minus in your aqueous solution to show the basicity. So the concentration initial, the concentration change, the concentration equilibrium for your hydrazine. And for the liquid, everything will be a dash from your initial up to your equilibrium because it's a liquid. Starting off with your N2H4, the initial is the one that we are looking for. Let's say I put an unknown Y. Y is the one that we are looking for right now. Okay? So initially, my product is 0. At the change, we know that the change is minus X because it's a reactant. It will be used or it will be dissociated into your product. That's why your product will become a plus and a plus. We are forming the product. Okay? So at equilibrium, it will be Y minus X. Over here will be X and your X. Okay? Simple. So, I'm looking for this one. But right now, we have two unknown. We have a X and Y. But we know that we are looking for the Y. We are looking for the initial of the hydrazine is how much. Okay? So, we need to solve the X first. How do I solve the X? Simple. Look at what you have. You're having the pOH. when you're having the pOH, we know that we can find the OH minus concentration. From the formula of pOH equals to negative log OH minus concentration. And we know that the concentration of OH minus at equilibrium is equals to X. Can you see that? And we have the pOH value. So substitute in your pOH value 4.25 equals to negative log concentration of OH is a X. Can you get your X right now? Simple. Alright? Solve your anti-log. Okay? So to find the X, and the way that you press your calculator will be shift log. Okay? Press your shift log and then negative 4.25. That is the way that you press your calculator. Okay? So your X calculated will be 5.6234 times 10 to the power of negative 5. And that is the X that you obtain. Can you see that? Alright? Simple. Next, how do I find the Y? Last step. You already have the KB value given. The KB value given over here is 1.7 times 10 to the power of negative 6. You have everything at equilibrium including the X that you just calculate. Can you see that right now? So you can write the formula of your KB. KB equals to the concentration of N2H5 positive times the concentration of OH minus over the concentration of your hydrazine N2H4. Substitute in the KB value 1.7 times 10 to the power of negative 6 equals to X multiplied by X over Y minus X. Do you have the X value? Yes, we just calculate the X value. So substitute in your X value. You will then have your 1.70 times 10 to the power of negative 6 equals to 5.6234 times 10 to the power of negative 5 square, Y square, because it's a X times X over here. Okay? Divide by Y minus X, which is Y minus 5.6234 times 10 to the power of negative 5. Okay? And since you only have one unknown, guys, you can find what is your Y, right? Knowing that your Y also equals to the concentration of your hydrazine initial that we want. That is your Y. Can you see that? So, your Y calculated is 1.9164 times 10 to the power of negative 3 molar. It's a concentration. So, it's a molar or mole per liter. Okay? So, this is a slightly different question where the question asking for the concentration of the hydrazine solution. Okay? And the trick of the question is, your hydrazine is a base, but the question giving you pH. So, the first thing that you do is you need to find the pOH. From the pOH, you can find the concentration of your OH minus ion. And the concentration of the OH minus ion proved to be a X over here in the ice table. So when you found the X, you can easily solve your mathematics and you can find your unknown Y, or you can find your unknown concentration of hydrazine at initial. Bear that in mind, it's a concentration, therefore your final answer must be a molarity. Okay?
TunePocket.com